So in this lecture, we'll learn how to implement a string copy function. This will enable us to see how we see the load byte, store byte operations used in an actual RISC-V code. The string copy operation will work with no-terminated strings. A no-terminated string is a sequence of characters, and the last character of the sequence has the value 0. 0 is called the no character. Here is a C code that implements string copy. What this C code does, it takes two parameters as input, the parameter x, which is the base of the target string, and the y is the address of the source string. So the string that is in y will be copied into x. There is an I that will be used as an index, is initialized to 0. And then inside the while loop, inside the condition of the while loop, there is an assignment that is assigning the value of y sub I to x sub I before testing whether that value that was just assigned is different from 0. If the value just assigned was not 0, then the index I is incremented and we continue the operation. If the index, the y sub I assigned to x sub I was 0, then we terminate. So that's the operation of this string copy. We're going to use these assumptions over here that says that I is in S0, x in A0, and y in A1. And some of you that maybe think about the register save and restoring convention, maybe you wonder why we are using S0 here. And this is just for illustration for this class so that we can illustrate the saving and restoring of registers into the stack. A more efficient version of this code would use, for example, T0 instead of S0 and not having to save and restore it from the stack. But this is just a teaching example to illustrate how we do that. So again, I will illustrate how to produce the assembly code for this program by doing a gradual lowering of the program through an intermediate representation. So the first statement of the program consists in assigning 0 to I. And then in order to do the assignment of yi into xi, I need to load the value of yi into temporary. Next, I need to take the value of that temporary and write into xi. And next, I need to ask whether the value that I had loaded is equal 0. If it is equal 0, I go to a label L2. Otherwise, I increment the value of I, and then I go unconditionally to the label L1. The label L2 will be the return statement for the function. We'll start lowering this code further, and the first thing that we'll notice is that I is supposed to be as 0. And the other thing that we'll notice is that I already have the value of yi into temporary t2. So instead of testing yi, I can test the value of t2 in the conditional. Doing this change results in the code that I have on the right now, where I have replaced I by S0 and I have replaced yi by T2. Next, I need to deal with the fact that S0 is in memory, and I need to load that value. In order to load a position of an array or from memory, what I need to do is to first compute the address and then use a load operation. Thus, what I'm going to do is compute the address ys0, and the address of ys0 is a1, which is the base address for y, and plus s0, which is the index. I'm not multiplying by 4 because this is an array of characters, and each character occupies a single byte in memory. Next, I need to do something similar for x of s0. I need to first compute the address and then store into that address. So computing the address of x of s0 will be the base address for x, which is in a0. And I add s0 because, again, x is an array of characters. And I use in that notation M of T2 or M of T3 or M of T1 are the memory positions of the given address. I use M to represent memory. So now that I have my code, I need to save registers and restore registers at the beginning of M. And this is what we usually do when we write assembly code. If you write on paper, you should leave some space at the top of the page where you're going to put the save registers instructions later when you find which registers you have to save and which registers you have to restore. So recalling the register calling convention, all the S registers must be saved and restored by the callee. None of the T registers or the A registers need to be saved and restored by the callee. So in this case, what I need to do is simply to save S0 because I have used it as 0. If I had not used it as S0, I would not need to save any registers in this example. Again, this is a teaching example. We chose S0 so that we are forced to save and restore, and we illustrate how to save and restore registers. So this is the code that we have produced. And now with this intermediate code, it's very easy to produce the assembly code because each one of those lines can easily translate into an assembly instruction. As shown in the slide here, first I save the value of S0 to the stack, then I zero S0. Next, I compute the address of yi, and then I do a load byte unsigned from that address to T2. Load byte unsigned would work just as well here, but whenever we want to make sure that the value that we have in the register is only the byte that we loaded, a load byte unsigned is preferred. Next, I compute the address of xi and I store then the value into xi. Then I ask whether T2 is equal 0. If it is, I'm done and I go to the end of the loop. Otherwise, I increment the value of I and I go back to the loop. And finally, I restore the value of S0 from the stack, and I have my returning statement. So this is the assembly code for that string copy function that I have at the top. And we have illustrated how we use load byte unsigned and store byte in this example. However, this version of string copy is not a version that I recommend that you write into C code. The issue with this version of string copy that I have here is that there is an assignment that appears inside the conditional. And the problem is that someone that's reviewing this code may miss that there is an assignment there. So a couple of versions that I could use instead would be something like this. So in this case, instead of using a while, I use a do while. That is exactly what this code is doing. But because I'm going to have the increment of the I inside the loop, and I need to test for the I position in the while test, I actually initialize I to -1, and I increment that value of I before I do the first access to the positions of X and Y. This way, when I come around the loop, I always will be increment I before accessing and then testing the correct value. So this might be a better version than the one that is on the top. Another version that I can use, it would be using a for loop. So for a for loop, the important thing to note in here is that the position 0 of Y, the first character for Y, is always copied into X. If that character was 0, then I had an empty string in Y, and I copy the empty string into X. So in this version, I do this first assignment for position 0 before I go into the loop. Now, when I go into the loop, I can test if the value in the position 0 was 0. I'm never going to execute any one of the iterations of the loop. Otherwise, I will keep making the copy until I find that I have done the position yi equals 0. So those are versions of string copy that may be easier to read than the one that we used in this lecture. So a quick recap of the second part of the lecture. We start with a C version of string copy. We show how we can step by step lower that version until we have intermediate code that is easy to translate into the assembly code for this instruction.